So, hello, welcome to all. It's very nice that you could make it despite the beautiful weather outside, a lot of sun, and I know you want to be outside, but let's enjoy for a moment our distinguished lecture series that I remind to you is a joint effort of the University of Helsinki and Aalto University. And in particular, the computer science community and the Department of Computer Science. And we are a very active community, the two universities working together. Recently, we have established the High Data, Helsinki Center for Data Science. This year, also the Finnish Center for Artificial Intelligence. So a lot of things happening, and to crown all of these nice developments, we are able to attract emerging stars from the research community here to talk to us about the trends in artificial intelligence. And it's particularly a pleasure to welcome Professor Nick Lane, currently at Oxford University. And Nick, I think, has been able to travel all around the world to come here, from New Zealand, and then through US, New York, and then England, Beijing also. So we really welcome his view on what's important to be looking at. For example, some of his themes about how to use machine learning and deep learning into computationally constrained environments, as we will hear. Nick, prior his position at Oxford, has been also at the UCL and had a joint appointment with Nokia Bells, where also important work in a project called DeepX has been done exactly in this area of deploying machine learning in computationally constrained environments. That also that work was awarded a Google Award faculty in machine learning, and also following several best papers in different conferences. I'm quite curious to know in the audience. I'd like to do a probe and a poll, if you follow me on this experiment. Who is from academia? Okay, from industry? Okay, so we have a good proportion of the both. And who is maybe in the area of ubiquitous networking and this kind of computing? Yeah, signal processing, machine learning. Okay, so there is a bunch of crowds that is not in these different areas. We will hear maybe from the question from which areas you are. Very good. Okay, so without no further ado, I'm really excited to listen to Nick's talks. I have seen just a glimpse of a few slides and they look fantastic. So now I shut up and sit down and let's enjoy the talk. Great. Nick, please.
Thank you. Second, how do I do this? Okay. Thanks for that kind introduction. As you would have heard in the introduction, the bulk of this talk today is going to be speaking about the work we've done towards squeezing different forms of machine learning, principally deep learning, but these ideas would extend to other types of machine learning onto constrained devices. And the talk also contains this theme of how of the importance of being able to do this for the evolution of these IoT, mobile, and wearable devices as they go forward in the future. Currently, I'm full-time at the University of Oxford, but I also maintain a part-time position at Bell Labs, and a lot of the early work in this talk, in fact, was done at Bell Labs in Cambridge, and some of the later works I go into a bit more depth have been done at Oxford, for example. But I've been giving talks like this for a while now, for the last 2 or 3 years. And initially when I started giving these talks, I'd always have to start with slides like this. And slides like this basically help motivate the need and the benefits of being able to bring what is state-of-the-art machine learning to mobile devices through typically examples of deep learning. So this one, for example, is the use of deep learning for speech recognition, and the example, the anecdote by which when Google first adopted these on the Android platform back in 2012, they saw what was at that point unprecedented gains in the word error rate. And it caused people like Jeff Dean to say things like, oh, this is the biggest single improvement we've seen in speech research in the last 20 years. Now, whether you buy that statement or not, it's certainly coming from a person who's at a sort of vantage point to really say that the use of deep learning meant a lot for what was actually feasible to put into production for things like speech. And this wouldn't be important if it didn't start to extend out beyond speech to things like object recognition, language translation, natural language processing. There was this avalanche, I'm sure many of you are aware of, where people are using a common set of architectures and algorithms for training these models and finding they were able to either outperform prior state-of-the-art or push forward state-of-the-art to the point that we could put into production systems that we haven't seen before. Now, for that reason, it became pressingly important to say, well, can we have these breakthrough results not just being used in the cloud for building really interesting, powerful web services? Can we start to have them pushed onto the edge devices? So doing speech recognition, object understanding, and so on, where the environments are their most complex. Right? So when we take the mobile device out into the environment and use it around with real people. And when I first started giving these talks, it would largely be sort of motivational. I'd try to motivate people as to why we want to do that. But what's been interesting is that in the last sort of 6 months, we've started seeing very strong commercial examples of the types of things that I've been talking about for a while. And so this is a product from Microsoft. It's called Seeing AI. It's got a lot of attention because it brings a variety of computer vision techniques that are state-of-the-art, and what's most important about it is that it runs predominantly on the edge device. Now, this is largely for helping people with sort of different types of vision impairment. You can download this app today, and then what you do is, like, for example, point it at a person and it'll do an image captioning task and speak it out so a person with some vision impairment can have a sense of what they're looking at. And so I thought as a good way to start this talk, I want to show you not a canned video from Microsoft, for example, of them using this, but of an actual user experience of using this type of system as a way to sort of start to give some hints in terms of how we could start to transform mobile devices and wearables by combining them with state-of-the-art machine learning running locally on the device. So let me just show you this video. It's just of an average person. Unfortunately, we couldn't get the sound to work. But this is one of these, YouTube user-first experiences. They would have just got this app, put it on their phone. So this is what the guy looked like in this particular case. And if I fast forward to 235, you can start to see what the app is capable of. So I'm going to play the video. You're going to see an image captioning task that typically would have previously been done only in the cloud, being done on a constrained smartphone device, and the results coming back relatively fast, and where the key interest here is not the actual fact that the image captioning is pretty good, it's the fact that we no longer have to take that photo, upload it to the cloud, have the user be worried about what a third party may be looking at, and being able to enable a mobile application to have fairly sophisticated forms of vision understanding in the wild. So let me just show you. Again, this is not a canned video. This is just an average user. I think they're in Dublin. He walks up, presses the button. You can see, I don't know if you guys can read that, but it says a large stone statue in front of a brick building. So it's a pretty decent image caption. He hasn't, again, this is not a case of the research student knowing what works and what doesn't. So it's a tough problem, and again, it's running locally. And it's through the use of techniques that have come up in the last 2 or 3 years that were adopted by folks in Microsoft that enable this to be possible. Ideas of quantization, use of low precision and deep learning, and so on, that enabled this to be possible. Let me show you the next example. So we go somewhere else, and you can see a green street sign sitting on the side of a road. Again, a pretty decent caption being generated. So again, it's early days. It's obviously, I'm not saying that this is an end killer application, but it's an example of the direction of where we need to go for, in this case, a smartphone, but I think it needs to be extended all the way down the ecosystem. So smartphones are actually kind of on the top of the food chain in terms of resources, but the type of things I'll be talking about in this talk are trying to bring this type of understanding and intelligence to IoT devices, fridges, watches, and wearables, and I'll discuss why we want to start to do that. So if we go back to the talk, I want to give you a sort of sense of history where we've come in the last 2 or 3 years, because it's been a very interesting sort of progressive pattern. So in parallel to people producing really powerful and interesting models that can, that are able to do certain tasks that can neatly map to different types of applications, and vision, audio, NLP are being sort of really interesting ones. There's been a parallel set of innovations being done by people I work with on the left-hand side, and also on the right-hand side, other examples of breakthroughs that have occurred that enable these models as they are produced to run on devices of varying complexity. So on the left-hand side, there's the work that we've done. So for example, one of the things that caught a lot of attention back in mid-2016 was we're the first group to show that you could run VGG, which is a very well-known, fat, heavy vision model, directly on a smartwatch. So not a smartphone, nothing was 2 gigabytes of RAM and so forth, but a smartwatch, just an off-the-shelf Android watch with a variety of techniques we invented. On the right-hand side here, I'm acknowledging some really other powerful trends that are occurring, both in algorithmic changes. So people have found that you can do a variety of techniques such as node pruning, using low precision and even binary networks to produce forms of the models that you are typically being seen in more rich, resourced environments like the cloud on these edge devices. And also it's important to know that in parallel, there's been a lot of innovation in the hardware sphere. So there's a tremendous amount of activity on building things like accelerators that are purpose-built for some of these algorithms, and there's been really interesting work in that space too. And so to speak in a nutshell, where we're heading is looking how we can start to understand how we can systematically overcome the barriers that exist today between when someone comes up with a brilliant new idea about how we're going to model a piece of data and have an interesting task being automated, and now allowing that to seamlessly migrate to constrained edge devices. And from my mind at least, one of the frontiers that we've been looking at in machine learning for a long time has been this obsession about accuracy and robustness of these models. I think looking forward, though, there's going to be a secondary aspect of this problem, which is, can we develop these same models that can run anywhere on anything, as a second criteria to understand if they're going to have impact. So what I'm saying here is that moving forward, when we assess whether a piece of a model or a new algorithmic innovation is going to have impact on the world, we have to not just only think about how is it going to sort of generalize across different types of people and environments, but its impact on the world is going to be much more thought about where can it be deployed, and who is it going to be able to reach? And answering questions such as how can we allow that to become more seamless is going to be very pressing, important issues for computer science in general. Now, if you want to start to think about some of the individual motivations as to why we want to do this, I think there are dozens. But one I'd like to highlight is that of user privacy. So if you think about wearables, for example, and the types of health information that they potentially may be able to give us, they're going to use information that's highly sensitive. So things like understanding someone's speech and using that speech to understand if they might have PTSD or stress or depression. Now, if we can push these models directly onto the device, we can present to users very simple mental models of how they actually operate and what it means for their privacy. So we can say to somebody, hey, this device is going to listen to your speech, that's going to make them nervous, but we can also say this speech never leaves the device. In fact, it's never recorded, it's never stored anywhere, it's on the fly, processed, and you're tagged whether you potentially have a disease, and only you get to know the outcome of that. So it allows us to do that sort of thing. There's also very system engineering important characteristics that become possible when you start to have this seamless migration of a technique that's invented without resources being considered and allowing it to push downwards. So currently today what happens is I might come up with an interesting model, it takes a lot of resources, and then there's a lot of engineering and a lot of PhDs need to consider how am I going to allow this thing to squeeze down into smaller and smaller sizes of memory and lesser amounts of compute. And as a result, you have this parallel innovation of initially a model is developed, and then there's secondary work to how we can optimize it further. If we have techniques that allow us to take the models and compress them in a variety of ways, reduce the amount of computation, increase the utilization on how they use the different compute resources on each devices, there's no need to do this secondary work. There's also issues of, for example, real-time execution or continuous sensing. Many of the types of devices that we want to build today are going to have to sense people throughout their day on a single battery charge. And there's no way that's going to be possible if you want to do these inferences continuously throughout the day and you have to have a cloud connection established all the time, right? But I think there's also a larger motivation here outside of these individual issues, and that's really thinking towards how can we build systems that really work in the wild. So if you talk to UBCOM researchers or mobile computing people, they'll have no end of various types of innovative applications that you see being shown at the top here that they want to enable. And they range from things like mobile health, digital assistance, up to large-scale systems such as doing types of urban sensing to understand pollution and understanding sort of stress throughout a city. And the problem is they know how to build the applications, they know how to map them onto the devices, but the accuracy of these systems just isn't good enough yet for them to be realized. And one of the key ways we can start to bring these two worlds together is going to be allowing us to bring to bear the best models that people have invented. So if let me see, here's my, right. And this is what this slide is talking about. There's basically this sensor inference chasm. So we know how to build the applications. We have the systems that have the sensor information that we can be used to realize the applications. But currently, if you look at them and say, for example, those that are in the literature, time and time again, you'll see this problem where as the system is scaled up in terms of population or in terms of geography, the accuracy of these systems starts to decline. And if you study as to why that's really happening, typically it's because the models that they're using are just too simple. Often, in some cases, there might be an existing model that would have made a lot more sense to apply, but it's just too resource heavy. So for us to move forward, we have to get to a space where we can start to use these techniques much more seamlessly. And what I'm really talking about here is being able to migrate away from wearables that do very simple single tasks, largely discriminative. For example, asking someone to wear a device and all it can tell you is how many steps you used through the day or how many hours did you sleep. Moving to a model where we can put onto the device a lot of reasoning capability and really extend that stack. So extend the sort of cognitive mobile stack that we can actually fit onto a wearable such that we can expand out the application space we can consider. We sort of it will enable us to think far more richly and broadly than we can think today, not just, for example, counting steps or so on, but doing far more complex tasks. And so one example of that, to ground this a bit more, would be, let's just think about the type of reasoning capabilities that we can build today for an autonomous car. So there are prototypes today, they're driving around. I was just in Arizona 2 weeks ago and I saw dozens of autonomous cars that you could call up just on your phone through Uber. Now, these autonomous systems are doing a lot more than the wearables we can see today, obviously, right? So they're navigating an environment, they're experts at this particular task, they're able to reason about how humans are going to respond. And that's the type of complexity of applications that I want to see us building for wearable systems in the future. And the only way we're ever going to aspire to do that is if we become incredibly good at understanding how we can squeeze machine learning techniques onto the device constraints we're faced with today. And that's a key motivation for what I'm doing here. So why is this hard? Well, one of the reasons it's hard is that when we're actually building these models, there's a tremendous disconnect currently between the model innovation that's occurring and the resources that they use. There's just a complete disconnect. So this graph is showing you just one single task. That's the ImageNet challenge. So the accuracy of these vision models is being shown on the y-axis. Along the x-axis, we have the operations required for inference. And then each circle is a new type of model that someone came up with. And so you'll see advancement occurring where we're going increasingly higher and higher in terms of accuracy. But the different models, for example, that come at different intervals there's basically no linear progression between how much a certain accuracy is going to cost us and the inference cost from that model. So, for example, VGG is operating here, in the sort of mid 70s to 75s and top 1% accuracy. But if you look at a more recent model, for example, such as ResNet 100, it's far cheaper and far it's far cheaper and it's slightly more accurate. If you go to something like GoogleNet or ResNet 18, it's less accurate and far cheaper. So essentially, no one is really sort of tracking or having a way to reason about the resource costs as they go about designing these algorithms. And that's because the tools are just not there yet. The thinking, the algorithms there that are available to people who design these systems today, who think about what's the next model architecture going to look like, does not allow us cleanly to understand what it's going to cost. So why is that? And that's because today, machine learning algorithms and the world of mobile embedded systems are basically two different worlds that seldom meet, right? So we have the algorithms on the right-hand side here. We have the resource constraints, and there's not a lot to connect them. If you think about the types of techniques that are out there, you might think of paradigms of training and inference. There's no connectivity there between that and the energy that's going to occur, the memory that's going to be used. What we need to move to is a place where there's an ecosystem of building blocks that are far more resource aware. And I think a nice way to think about this is if you think about how compilers and the targeting of different embedded devices exist today. People write high-level code, low-level code, and there's a complete ecosystem of different ways of compiling this to intermediate representations that can then target different types of resource constraints with different levels of tightness. None of that exists today when it comes to training a model or when it comes to designing or exploring a certain space of a type of model I'm going to build. And that's the type of software ecosystem we need to reach. But it's also going to take a lot of research into how we can build AI algorithms that are resource-centric and how we're going to appropriately map these onto the different types of hardware resources that are available today. And so not just accelerators, but also commodity GPUs found in mobile devices, also how we're going to get the most out of our DSPs and so on. So we have to sort of start to move forward towards having a complete end-to-end ecosystem that allows us to have a lot more resource awareness of when it comes time to design the type of algorithms we're looking at doing. And so the rest of this talk, I'm going to be focused on work we've done on how we can start to build different forms of AI algorithms that are resource aware, and how we can start to also build software systems that are able to sort of reason about the resources required by these algorithms and map them to the hardware availability in terms of constraints. And before I move forward, I also just want to highlight that a lot of this thinking seems to be pointing towards the big game in town being constraints and squeezing and pushing things down. But really there's a broader message here of efficiency. There's a question of being able to come up with algorithms that are much more able to efficiently use the resources we have today. So here are some examples of different types of efficiency, not about squeezing down, but about what happens at scale. So it's talking about examples of building large-scale training algorithms for different types of systems you've heard of, and just the sheer amount of resources that are currently being used to do many of the things you've heard about. So if you look at the third bullet point here, here's AlphaGo. So this is a very celebrated example of a powerful type of machine learning that's enabling, beyond human level playing of a complex game called Go. What's often not mentioned is that to pull these things off requires nearly 2,000 CPUs or 280 GPUs. And every time they play a game, we're talking about 3K worth of electricity. And not only is that a huge problem for us in academia about how we're going to compete with this sort of playing field, but it also starts to pinpoint that efficiency is not only an issue for how we're going to squeeze things down, but it's an issue that we're going to have to consider as we start to build larger and larger models that are capable of more and more things and start to be able to consume more and more pieces of information. Right. So the work that I lead at Oxford considers what I call a machine learning systems agenda. So essentially looking at the intersection of machine learning and systems. We do a variety of things, but today I'm speaking predominantly about efficiency machine learning with respect to low resource inference only, not training. We're working on those ideas right now too, but I'm going to talk about results largely on the inference side. And I want to talk a lot about what our approach is to this sort of general set of problems. So one key approach that we take is looking at existing paradigms and algorithms. So, for example, how do you train a model? How do you represent different types of models that you want to use in a system? And how do you then execute inference? And then completely rethinking each of these three different types of building blocks with the notion of being able to reshape how those techniques, for example, how does an inference use memory across throughout time? Or how much memory does a particular representation of a model take? And starting to rethink what those things are with respect to more severe constraints. And so a lot of the work we've done works as follows. We want to come up with what I call an algorithmic building block that is enabled, that it allows to be applied to an existing model, an off-the-shelf model, and then it has a core idea that enables us to reshape, for example, memory or compute. And so then this slide is showing on the left-hand side an original model. So you might have a pre-trained model such as AlexNet or GoogleNet or so on. And then we've come up with different ideas about how you can reshape that model towards constraining the amounts of computer memory it's going to require. The reason we take this approach to start with is that there are no games to be played, right? So it's not the question of we're training our own model, you've never seen it before, you have no idea about what the accuracy and the performance is going to be like. We get to use our techniques against a familiar model like VGG or anything, and then show you how much we can gain. And I'm going to talk about just one of these techniques because they're starting to get a bit old here, but it's a good example of the type of work done in the space. And specifically, it's compression by the way of inducing sparsity through sparse coding. This work was done at Bell Labs. And it also gives me an opportunity to give you a set of insights as to why these models can be so expensive. If you weren't so aware. So one of the key problems is that if you're looking at a deep learning model, for example, that's doing something like recognizing hello world from an audio signal, if you build this model through a set of fully connected layers and you look inside it, for example, that node being highlighted here is fully connected in the sense that all the other nodes in the prior layer are going to have to be connected to it. And for that sort of notion to be expressed inside the model architecture, you're going to end up with a data structure that might look something like this, right? So you have an n-by-n matrix that allows a set of nodes to be connected to the prior set of nodes. Now, the huge side effect of that architectural sort of design is that you can have even simple models using hundreds of megabytes, which is a complete death if you're thinking about deploying this to an IoT system. And so this figure is showing us a graph where on the right-hand side is log scale of memory. On the left-hand side of this graph, we've got different types of architecture. So many of you might have heard of probably AlexNet. And then these lines here are different IoT platforms or different types of mobile platforms. So you can see, for example, this black line here. This is the DSP that exists on a Snapdragon 820, and which has a memory footprint of just 8 megabytes. And remember, this is log scale, so you can immediately see an off-the-shelf AlexNet model used for object recognition is completely blowing through the memory requirements of the system. And one of the key reasons for that is this is the overhead of having to express these fully connected layers. So one of the things that we came up with was this notion of being able to express this connectivity through a combination of, well, essentially we're going to approximate the original connectivity between the two nodes with two other matrices. So we're going to basically factorize the matrix into two other parts, and then we're going to have a sparse coding technique, learning the dictionary, and then we express the original fully connected network as a sparse matrix. So when we actually use it in practice, I just won't go through the details, but When we use it in practice, it looks something like this. So on the left-hand side, you have the original fully connected network. This technique is going to come up with two new type of matrices that are going to replace the original fully connected matrix. And because one of them is sparse, we can save a lot in the representation size, and actually, unusually, we're inserting another layer as a means to also reduce the amount of computation required. Essentially, this newly inserted layer is itself a dictionary, and then we're using this dictionary to express the prior connectivity. Now, there is some loss of accuracy in this type of technique, but as you'll see in the results, we can manage those quite effectively for quite impressive gains in the types of memory these models take. But before I show you the results, I also want to sort of highlight the other type of bottleneck that you encounter in these networks. So that type of bottleneck I just discussed was largely grounded on memory. There's also huge amounts of bottleneck in terms of computation. Now, if I want to pick an example of the type of the source of computational bottlenecks, a good place to start would be the convolutional layers early on in a network. And so, for those of you who are not familiar, in a convolutional layer, you're going to have many of these feature maps being applied time and time again to the earlier layers. And so, you can have in a dense network, hundreds and thousands of these convolutions being applied time and time again, and these can cause a huge overhead in terms of computation. And so, what we did was come up with a complementary technique that combines with this memory compression method I mentioned earlier, essentially that looks at separating the convolutional feature maps into 1D versions that when you apply them iteratively, so one after the other, will approximate the use of the whole feature map. So that's the key idea. Can we come up with a 1D version or a pair of 1D versions that when you apply them consecutively will approximate the use of the complete feature map? If we can do that, as you'll see in the results, you can start to also reduce the computation required when doing a very similar set of operations to the original set of convolutional layers. So now, let me show you some examples of just using these two type of techniques. The aim here is we're going to have a degradation of only 2 to 4%. And then this is targeting the use of VGG. And this figure is showing you the gains both in terms of energy and latency. The colors map to different platforms. And I want you to look at just the blue one. So this is this blue set here, because that's the Snapdragon platform that you'll find in many off-the-shelf commodity smartwatches. It's the Snapdragon 400. And then this is what happens when you have the original VGG sort of very carefully hand-implemented running on this platform. So you'll see latencies getting up towards 1 minute for processing one image. So that's after a lot of hand engineering to make it actually work and do a lot of paging in and out. Then you'll see what happens when we start to apply these techniques one after the other. So if we have the sparse coding technique that's really aiming at having to ameliorate a lot of the sort of memory bottlenecks, we can start to really see this large shift, right? This log scale shifts in latency and energy. And you can see the same thing happening again once you in combination also apply this combination convolution separation. Now, the reasons why you might want to do that is for enabling the type of scene understanding that we saw in this celebrated Microsoft application, but occurring on small wearable platforms. So, for example, you could have VGG doing something like object recognition on anything built from this Qualcomm Snapdragon 400. So this is an example platform that we built from it, but you also find them, as I mentioned, in commodity smartwatches. Now, if we look lower on the food chain, even below a Snapdragon 400, so below what a smartwatch is typically sort of aim at in terms of resources, you start to enter the realm of microprocessors. So things like an ARM Cortex M3 or M0. So this is the scale of processor that you'll find in sensors that you might put in the home, maybe also the things you might have like a toaster. Now, if we want to enable something like a toaster to have the capabilities of doing things like speaker ID or hotkey word recognition, so similar to what you'd find in a smartphone. So as you know, the hotkey word recognition, you say, "Hey Google," it can answer you. You can start to use that as a user interface. If you want to enable that to happen locally, you're going to find some pretty severe resource constraints, because we're no longer talking about hundreds of megabytes or tens of megabytes, but we're down to talking about 32 kilobytes and 16 kilobytes of sort of operating RAM. So we can use those same techniques on a completely different model because we only work at sort of the architectural level. These are results assuming the same specification of speaker ID that came from a recent Google paper. And then I want you to focus on the, let's see, yeah, on these, it's red and teal colors. So this on the far left-hand side, on the far right-hand side. And you'll see in terms of latency and energy, again, by applying the type of techniques I'm talking about, we can shift the performance, for in the case of the M3, from being far beyond a minute in terms of processing, recognizing who was speaking, to down to 1 minute. So you'll notice that these are not ready for prime time. It's hardly reasonable that it would take your toaster to understand who's speaking after 1 minute. The real takeaway here, though, is the fact that we can do it all. And of course, that's sort of future work to be able to understand how we can start to push it further and further down. But again, it's working towards how can we have what I call smartphone level types of audio understanding being available on the smallest of possible devices. Now, this generation of techniques are actually, as I mentioned before, looking at how do you apply them to existing pre-trained models where the architecture's already been fixed. Another important process towards allowing us to have models that have much better energy, compute, and memory footprints are inventing those from scratch that come out of the box with a much better awareness of using far less resources. And towards that end, there's been a lot of work in the last sort of year to having different forms of architectures that can maintain levels of generalizability that are still good enough for doing state-of-the-art performance, but are also inherent from their design have important types of resource trade-offs. So now I want to shift gears slightly and talk a little bit more about a model that we invented that we call deterministic binary filter networks, or DBF net, and how by inventing a different type of convolutional network, we can not only still have fairly good types of accuracy, but we have very important types of abilities to trade off resources through the design of the network itself. So the network I'll be talking about today, DBFNet, there's potential here for having really high performance in terms of inference and training time. Today I'll be speaking a lot about how it can be applied to image and a little bit to audio at the end. But the most sort of interesting, at least from a systems point of view, is this, it includes inside it this seamless ability to be able to trade off large amounts of memory for small amounts of compute. So what I mean by that is we started looking at trends and building deeper and deeper networks, and we realized that ideas of being able to compress these things are eventually going to start to fail. You're going to reach a hard limit about how far you can compress these things down and still have good levels of accuracy. So we asked the question, what could we invent that would do similar tasks that allow us to still have deep networks, but allow them to start to have applications still in these constrained environments. So the problem is that if you look at things such as ResNet 34, and you look at any of these layers, again, you have this big bottleneck of convolutions happening at each single layer. Now, one way to go forward in terms of lowering the resources that these types of deep networks have, that people have been studying, is moving from real precision in terms of the feature maps that we saw earlier to binary representations. Now you lose a lot on the representation side, but if you can train the network still sufficiently, people have found that you can have pretty good types of accuracy, and then you have huge amounts of gains. So trivially, obviously, you're going to go from a situation, if you're defining these different parameters in the feature map by real precision down to binary, you're going to have a 32x gain in terms of the representation size just off the bat, if you can manage to train it. And because also, if you're using bit level types of representation, you can do the same type of thing of doing convolutions, but you can replace them by just simply doing XNOR and bit counting and still have the very similar operations occurring because you've gone to just single bits rather than floating point numbers. So that's being done before. What we wanted to try to do was look at a new way of using binary filters that would have a secondary impact in terms of resources. So specifically, we said to ourselves, can we come up with a convolutional network where instead of learning these feature maps, even though they're binary, instead of learning these feature maps directly from data, what would happen if we started to have a set of feature maps that are binary that are deterministically set ahead of time? So we set them ahead of time, we've never seen any data, and then our challenge is going to be, can we find a set of coefficients that allow us to combine these feature maps and then result at a floating point layer that would be good enough to actually learn the types of things we need to learn at different layers to do things like object recognition and so on. And if you're not familiar, some of the intuition here would be that if you pick your binary basis well, if you have a set of criteria ahead of time that allow you to sort of know that if we have, a large number of binary bases that are orthogonal, you can actually do a pretty good job of representing any sort of image through a series of very small number of coefficients and those binary bases ahead of time. So it's not surprising that you can do that, but this is an actual example based on real data. So this is the original image using carefully selected binary basis and a small number of coefficients and reconstructing the image, just to show you the power that you do have in case you're not familiar. And essentially the design of the network is such that we insert these binary deterministic binary filters throughout the network. At runtime, you'll need to construct these. You need to construct the full feature maps and use them, but you can have various types of architectures, such as those that have come before, things like ResNet. You can use things like a SqueezeNet and so on to combine this idea and build any type of network that you want to achieve for different tasks you have in mind, but they can be reused. The other important property here, though, is training is much the same as usual. You're going to have a forward pass, push them through. You're going to reconstruct the feature map, have your loss, and go back. But the key point here is that we don't have to learn the basis from scratch. We're just going to learn the coefficients that join them together. And so if you only have to learn these small number of coefficients, there's a potential here to also be able to train these networks in a much faster time. But what's really interesting, though, is what you can do at inference time. So because these things are static, rather than have a situation where I have an embedded device and then sort of on the memory side I have to lay out this very dense network and then I run inference over the top, I can get to a situation where I can do this, where I can have a small algorithm computing on the fly the binary basis, and then from disk or in memory I just have to load the learned characteristics. So learn the learned coefficients. So remember, at inference time, what I'm trying to do is I have an image here. I'm going to need these learned coefficients, but instead of loading instead of having the binary filters in memory, I'm going to generate them on the fly. So essentially in the design, we found that we can do a pretty good job of using existing algorithms such as OVSF, which can be computed very cheaply, particularly when you have sort of a small microprocessor on the side of a DSP, to generate these dynamically based on what you need, and then replace completely the need to have them laid out in memory. And that's one of the key trade-offs here. So when you start to have such a sort of unusual type of architecture that has promising sort of properties that could potentially be really useful, one of the key questions you ask yourself is, can we actually learn anything with this thing? So that's what this result is showing us. This is the main graph here is top 5 accuracy for ImageNet, and it's being compared, this DBFNet, which is on the extreme right here, it's being compared to AlexNet for just sort of completeness, since everyone is very familiar with AlexNet type performance. And then it's being compared to 2 types of constrained architectures that have been developed over the last few years, MobileNet and SqueezeNet. So these are not binary networks, but they're architectures that have been designed specifically to have low footprints in terms of memory and compute. And they're also comparing against other types of binary networks, so XNORNet being state of the art. And what this figure is showing us is that even though we have this network that's a bit harder to train, that has these very important largely runtime benefits in terms of resources, it's able to sort of perform fairly well against other types of networks of its type. So accuracy is not being lost significantly here. On the lower parts of this figure, I show performance for DBFNet on Sapphire 10 and SVHN, but the real takeaway here is ImageNet. The takeaway is that our results are still fairly accurate. But then we have all these additional benefits in terms of runtime performance. To further illustrate and show you something brand new, last night I was talking to my student Javier, and luckily we're 2 hours ahead of time. So it was about, I don't know, I think it was 11:30 at night. It's still early enough for him to do something. And I said, do you have any of those results that could help to prove whether even if using these DBF filters are good when you have non-constrained architectures? So I asked him to look into what happens if we just have a ResNet architecture, and we replace the filters inside that architecture with these DBF net filters. And that really would start to answer the question whether this design of a filter can start to learn adequately and still have good levels of accuracy. So the earlier results are about having a constrained, smaller type of architecture. We're going to lose a bit of accuracy. Here we're looking at architectures as originally defined, so ResNet and SqueezeNet, so much larger. And we're asking the question, if I just replace the original filters that are full precision with these binary filters, can I still have similar accuracy? And the answer is yes. So if I highlight here this figure, it's a bit ugly, I'm sorry, it's only for Sapphire 10, but for each row where it doesn't say DBF, it's the original architecture as originally defined, and the second row that comes after it is the exact same architecture, but we've slipped in our idea. And the takeaway here is that we're not losing a lot in accuracy, at least for this small experiment. So again, I'm showing you here that in a constrained setting, we're able to have good performance gains, and looser settings will still be able to learn significantly and have good levels of generality. So if I just if I move forward. I wanted to show you one other really interesting new result was those results here are for images. The question is this architecture also able to do things such as learn other types of data? So this is for hotkey word recognition, so doing things like Hey Google. We're comparing against ARM has been doing a lot of innovative machine learning recently, so they came up with the state-of-the-art performance of a network that's optimized for their ARM processor. So this is the ARM M7. And then they recently published a paper on arXiv that shows their performance. So they're at the top corner in blue, is DSCNN. And then so what we're doing here is training the same type of architecture. We're calling it binary CMD for different sizes. And you can see that we're able to basically be half in terms of model size, so a big gain in terms of model size with very little loss in accuracy. If you can tolerate a loss of about 4%, we can give you half as much as model size when we use this type of architecture. Now, very briefly before I sort of start to wrap up, I want to highlight one other further part of this puzzle. And so that is not just developing different types of algorithmic building blocks that let you reshape existing architectures and not new types of models, but it's asking questions such as, can we design new type of system components? So very familiar things like compilers, schedulers, maybe end-to-end systems, maybe memory managers that include this type of techniques. So these techniques are building blocks. What happens when we start to include them in familiar system-level components? And that's something we're very excited to doing. The idea is basically showing that you can build system components such as things like schedulers when they're targeted for things like sensing algorithms by incorporating these building blocks and allowing it to have outsized performance gains at the system level in terms of design. So I want to show you just one example of a scheduler. It's a scheduler we call Leo. This is in collaboration with the University of Cambridge. The idea here is have a scheduler that has the sort of semantic awareness to understand how it's going to decompose different types of end-to-end machine learning sort of pipeline for doing things like image and audio, and then give the scheduler enough awareness of how it should schedule these components onto different types of hardware and also sort of compress them as needed. And so there's just one takeaway result. So this is for an audio platform. It's running on a Snapdragon 800, so something that you'd find in mid-tier smartphones today. The main figure here is showing you the lifetime of this device if we're doing a series of continuous 5 different types of audio sensing. So it's doing speaker ID, emotion recognition, stress, and ambient sounds, but we replace the scheduler with one that's able to sort of understand how it wants to decompose these particular modules of machine learning and put them onto, for example, the GPU, the DSP, the CPU, at times offload to the cloud, and doing so with an awareness of the techniques rather than this generic scheduler that you have in an operating system today. And the takeaway here is that we can get this device to last 4.8 times longer. So this is the lifetime of the device. This axis here is the amount of talking that it overhears throughout the day, because that's a very sensitive component to its performance. The green line is the Leo scheduler. The higher you are going to the top right, the better you are. And then as a comparison, this yellow line is using all the Leo techniques, but it's doing it statically. So you ahead of time you say, what's the optimal assignment of this particular workload? It's not sensitive to the data coming in, whereas Leo is able to run a true scheduling algorithm where it's understanding as the data changes, and you can see the gains that you have when you start to inject these techniques into system-level components. So with that, I'll start to wind down. But just to summarize, sort of the heart of the area is really asking ourselves, how are we going to start to remove the barriers that prevent, instead of the machine learning being able to sort of seamlessly transition onto constrained devices. And one of the reasons I think this is so important moving forward is that this is going to be a key type of technique moving forward that allows us to transition from devices that do very simple, just sort of discriminative tasks, so things like counting steps, counting how many hours I slept last night, to devices that are far more powerful, far more rich, able to do things such as collect different types of perceptual data, understand what it means, have some level of common sense, and do reasoning on top of that, through which we can start to build sort of novel mobile applications that really incentivize somebody to wear these things 24/7. And to allow us to do that, we're going to have to bring together two worlds that seldom meet, that of machine learning algorithms and the people who understand deeply mobile and embedded platforms. So with that, I'd like to thank my collaborators from Oxford, Nokia, Bell Labs, and Cambridge, and I'm happy to take questions.
So thank you very much, Nick. Sorry, I got distracted trying to open the microphone. So now we can have some questions, and let's see, I have a couple of questions myself, but I want to see if somebody from the audience wants to beat me. So my question would be, it's a double question. The first part of the question is, so why should we, summarizing, because I think it was in the presentation, why should we care about computing in these constrained environments in the mobile in mobile devices? And the other more difficult question, a provocative and exploratory question, is it seems that many times when we work with mobile computing, we are trying to replicate what we already done in a different environment, and just trying to not lose, I don't know, accuracy or things like that. So, but isn't there something new we can do? And it would be interesting to hear your thoughts on the two questions.
Let me go to the second one first.
Yes.
So with the second one, I think we need to start moving away from, I was trying to mention this in the talk, but I want us to start moving away from this notion of approaching the problem by simplifying what's going on, and rather think about how do we increase the utilization that's happening on the device. So if you open up, as an example, at least in terms of current practice, if you open up a smartwatch and you see, how the core is being used, you often find that 3 of the cores are completely idle, even though there might be a heavy sort of speech workload going on, because that's the Android task scheduler, and the way that it's decomposing that workload is completely oblivious to how it should maximize performance on a CPU. So I think one important thing for us to move forward is to go away from trying to simplify algorithms, because then we actually run into this problem where they just don't work well enough. Because actually, in mobile situations, those are some of the toughest problems we have today. So we can do it, and interestingly, I think we can do this across the stack. So I think if you're a hardware person, you can start to invent brand new processors. But even just above that, it's an incredibly hard job in terms of how do you get the most out of a particular processor with respect to a certain machine learning algorithm. We've done a fantastic job of that, perhaps in sort of server class GPUs. But there's a lot of work to be done sort of across hetero cores. So how do you combine a GPU and a CPU and sort of seamlessly? If you go up a bit further, there are system components we need to invent. So for example, memory management that will allow allows us to do less cache hits on a particular model by shaping its layers. And if you go one further up, it's in terms of design of models themselves. Some of the things I was showing before. Can we think of a way where we design models from day one that is the sort of ability to trade off the resources they use? I guess if there's no more questions, I can answer question one.
Yeah.
But
questions from the audience here, Leo. And you're invited to say your name or anything you like about yourself.
So I'm Leo. Hello. So one of the things, if you kind of totally embed the machine learning to a mobile device or something like that, so one of the benefits, of course, is that you don't have to have a communication to the cloud anymore. Sure. Because you kind of, and that's very often the one that really uses the energy. But of course, you lose one part. It is that it is this data gathering activity. So it is coming onto it. So any comments on that? Because you kind of stop learning from your users after that you do it. So
I love that problem because it's a completely new playing field for us to think about. What Leo's sort of pointing towards is, hey, if in the future everything is done on the edge and it's all the inferences done locally, then there's no upstream of data. And currently, if you think of other types of services, things like Siri or whatever, there's a lovely opportunity for those people to explore what's going on with the data, perhaps refine the models and push it down. But once we move forward and we understand how we can push it to the edge, there's going to be another secondary set of problems all across the ecosystem of building machine learning that's going to ask us questions as how are we going to train. So there are many different interesting ways. So the obvious thing that people are trying to do right now is sort of federated learning, where you push a bit of learning to the edge. Maybe you can do some fine-tuning on the models. Something I think is a really interesting direction, though, is some sort of hybrid, where maybe you have some sort of offset cohort where you get a bit of initial bootstrap data, but then you have from your edge devices soft signals about when they're making errors or not, and you somehow include that into the training process in terms of how do you improve the model going forward. But it's not only just about training. It's going to be questions of, like, how do you even know that the model that you push to the edge is actually the one that's processing the data? When you live in a cloud scenario, you have this nice ability to observe what the model is. They upload the data so you can see the data as what it should be, and then you know what the result is. If you think in the future, what we're going to have is this situation where the devices are telling you what the outcomes are, and you need to have the ability to sort of know for sure that the model you expect to be running locally is the model that they ran. You also need to have the ability to know that the data they put into that model is the data you expect. So there's really nice, interesting sort of privacy and software system techniques that allow you to sort of attest to the quality of that model. Perhaps using sort of trust zone type of techniques, for example, need to be moved forward. So I think there's a whole lot of interesting, fascinating sort of system machine learning techniques that are kind of need to be invented once we can get to the edge.
Thank you. Here, Vetteri.
That's fine. Two different questions. First of all, about you said that you used about 4% in accuracy, what you gain with compressing the model or decreasing accuracy. Have you looked at where that loss happens? Do you lose generalizability in that sense, or what's the kind of cost of the additional errors? The other question, that some of the techniques that you were using for compressing the models are kind of designed also for looking at patterns which don't necessarily have labels or something like that. So can you perhaps use that to reduce the labeling effort for constructing these models in the first place, thus helping maybe the privacy aspect as well?
So for the first question, it's a really good one. So we haven't done a systematic study of like where those losses are happening. So I think it would be important moving forward. And to be honest, to the best of my knowledge, nobody has. So there's a cottage industry of different techniques using low precision and so on, where they can measure through the data sets of what's actually where the loss is, quantify that loss. But I haven't seen a systematic breakdown in terms of like what's happening per class, or even in terms of generalizability when you take it to a new environment, what exactly is failing. So I think someone really needs to do that, and we have not. I don't know of any result that shows that yet, so someone should do that. For the second one, I guess you're talking about, so some of these techniques we're using have also been used for doing sort of unsupervised learning to some degree. And your question was, maybe they could be used to also allow us to do the learning with less labels. Yeah, so I guess, I don't have a direct answer for that question, but I can make an observation, and that is that one of the really interesting things about the model design that I talked about, this DBFnet, is that it requires fewer parameters to be set. And so what we're hoping to see moving forward with some additional experiments will be to show that because there's fewer parameters to be set, in theory, we should need less data to learn similar concepts versus an over-parameterized model, over-parameterized conventional model where you want to set all these different parameters. So hopefully if we can start to reduce the complexity of these models, we can start to reduce the dependence on large amounts of data to some degree. But that's my only comment for your much larger question that I don't have a good answer to.
Thank you, Nick. So, if there are no other questions, we have one final question over here. Thank you.
Hi, this is Hongli Zhang from Denver University of Technology. Thank you for the nice presentation. So you have presented the different techniques that from the architecture that can squeeze the network and make it faster. And what I see that is like from the industry that the hardware company, they are actually developing fast. There is the TPU and Intel is doing something there. Mm-hmm. So how do you foresee in the near future that will it be one day or that comes very soon that those techniques will not be necessary, so that they are doing, let's say, a deep learning chipset. So they probably can do a ResNet chip or the DenseNet chip. So then you don't need those techniques. So how do you see that? And do you think that is actually coming soon?
So what I'm certain of is that we're going to see certain model architectures done very cheaply. So even right now, for example, I was talking to Pete Walden, he's the head of TensorFlow for Google in terms of mobile and embedded. Some of the things I recently did with Qualcomm was to partner with those folks to have an end-to-end tool chain that allows you to go from TensorFlow and program directly onto the DSP of a Qualcomm Snapdragon. So I think for many architectures that you're familiar with, it's done. So if you want a watch, you want a phone, they'll be fine. The question is that hardware innovation typically lags a lot the machine learning innovation. And if you talk to the hardware folks, it's actually pretty hard to come up with accelerators that have these really super great energy profiles and in sort of runtime profiles that can then truly generalize to a variety of different architectures. Typically, they have to target a certain domain of architectures they can run really well, because it makes sense, right? They're basically building a purpose-built processor. So one of the difficulties moving forward will be how are those folks going to generalize to other architectures? They're going to have lead times of 3, 2 years, 5 years, yet machine learning folks are going to come up with models much, much faster than that, so they're completely screwed. So what happens is that we're going to have to sit in the middle. We're going to have to develop software techniques, algorithm techniques that allow them to be decompressed, that can bridge the gap between hardware accelerators, which are always going to be in play for things that are super dominant, but bridging the sort of latest innovations and allowing them to be possible on the edge device. That's my answer to that. But I think that the key is how can we go forward about enabling accelerator hardware to generalize much, much better. And we can do that, I'm certain, through cooperation with hardware folks and software going forward, because that's the key sort of holy grail.
So thank you, Nick.